Okay, we're back with chapter 4, the Bernoulli equation and pressure variation. This is section 4 on acceleration. We're going to define acceleration and talk about how to look at it along a streamline. And the most important thing is we're going to define some terms, the local and the convective acceleration. And these are part of our attempt to look at the flow field in the Eulerian approach. So let's skip through sections 1, 2, and 3 and get to section 4. So acceleration we know is defined as being the change in velocity in time. And what we'll see is we can express this velocity in a couple of different ways. And in particular, we're going to express it in the Eulerian approach in this section. And so, but let's try to get a physical feel for what is happening when in just a given situation. Here we have a figure that shows the flow around a sphere. And so we're looking at the flow field here, a constant flow field, a uniform and steady flow field coming in here. But what happens when the flow encounters an object such as a sphere? The flow needs to slow down as it approaches the sphere, and then it'll start to flow around the sphere. We don't see the flow lines going around this, but we can certainly visualize that that's what happens. But what happens is on the central streamline here, the one that goes right through the center of the sphere, or would go through the center of the sphere, that's called the stagnation streamline. And what we'll see later on is that this velocity actually goes to zero right here at this point of the sphere. And so this velocity coming in, this basically along this streamline, has to start slowing down. So when the velocity starts to decrease from its uniform value out here in the undisturbed flow to this point here, to the stagnation point, the velocity starts to decrease, and so the fluid actually needs to decelerate. So when a particle is changing speed, there's a component of acceleration tangent to the path. That's very important. So speed is going to be measured tangent to the path or a streamline. And so we can look at this in a couple different ways. First of all, over here, you can see we have the tangential acceleration again. And so if the speed is changing, that tangential acceleration is gonna cause a tangential acceleration. But let's concentrate first over here on the left. And what we have here, this shows a particle moving along a curved streamline. And even in this case on the left, case A here, even if the speed is constant along here, so that the tangential acceleration doesn't change, we do have acceleration caused by curvature. So if a particle is moving along a curved path line, there must be a component of acceleration inward towards the center of curvature. And so we know this from physics when we did circular motion, that we have centripetal accelerations. So what we'll find is that we will have an acceleration inward along this path, and then somewhere along here it'll actually go to zero, and then as we go around this curve we will actually have some centripetal acceleration in this direction, inward towards to the curvature. So we realize that we have to deal with both normal and tangential components. If we look at a more complicated case over here, if a particle is also changing speed as it goes along this path line, then there will be, as we saw in the previous example, if there's a change in speed, there will be a change in the tangential acceleration. Then we will have, in addition to a normal component to the acceleration, we will also have a tangential. So let's try to write this out, and we're going to do this in a pretty explicit way. We're going to take our normal definition here of the acceleration being dv dt. but we're going to express the velocity in this way. V is basically, this is a scalar V. This is basically the speed, and it is going to be in the tangential direction. The velocity will be defined that way. So basically the speed, even though we'll have accelerations, could have accelerations in two directions. We determine the speed to be basically the velocity, the scalar velocity along this path, along the tangent. And so we can express this just in terms of calculus. We can just take this we can just substitute v this v here, the scalar v times the tangential direction. We can substitute that in for dv dt, and we have the integral of dv dt here, the scalar dv dt, times the tangential velocity through the chain rule here, plus v times the derivative of the change in the unit vector tangential. So we can also have either one of these things can be changing in time. And so we need to, in fact, and it's important to note that the unit, that any change in the tangential vector in time is not due to a magnitude change. Remember, u is a unit vector, so the magnitude of u is not changing. In this case, it's actually the direction. So if we go down to the right here, we can see that the change in the tangential vector with time is just v over r. That's going to give us, we'll see, we see that if we multiply v times v over r, we get the centripetal acceleration that we probably have seen in physics. So this change, this term right here, basically is a centripetal acceleration, and it gives us a term v squared over r times the normal vector. So we have a way now of determining when we have this curvature, this curvature, this normal acceleration is going to be related to the curvature. It's going to be v squared over r, where r is the radius of curvature of this curve. And v obviously is the speed along of the vector. And so if we also take dv dt and go down the left side here, we can again use the chain rule. We know that v is a function of both location s. Now this could be x, y, or z, and z, and also time. And so we have to take the partial derivative here. It's very interesting to note that we have to have these partial derivatives when we use the chain rule in this case, because v depends on both of these. So we have dv ds here, or del v del s, where we're holding time constant in this case, and we're just looking at how these spatial changes occur in the velocity field. And then we would multiply that by ds dt. Note that this is just capital V, so that comes down here. This term right here becomes v times del v del s. And we also have, through the chain rule, del v del t, where we're holding space constant. Now this is very important because this is actually very clearly the Eulerian approach, because we're holding space constant and we're looking at the velocity changes in time at particular points. So so that's a nice way of understanding part of what the Eulerian concept is about. And so when we work all this out here, this term becomes v times del v del s plus del v del t. And that's all in the tangential direction. So we've basically taken our acceleration, but since our velocity is a function of both space, s, and time, we get this more complicated version of the acceleration. And so we what we do in fluids is we take these terms and we call them both the local and convective accelerations. And so basically, let's take a look at this del V del T term. This is what's the local acceleration is. And I mentioned before, this is just the rate of change of velocity while we're holding position, or S, X, Y, and Z constant. So this is an Eulerian approach. We're holding position constant and we're watching the velocity change from these locations. And then the other two terms, the V times del V del S plus in the tangential direction, plus the centripetal acceleration V squared over R in the normal direction. This is what we call the convective acceleration. And these are going to contain variables associated with the fluid motion, V, S, and R, as we can see. So we've got definitions now. If we're given V as a function of both position and time, we can integrate that through a partial derivative with respect to time to get our local acceleration, or we can combine both these terms to calculate the convective acceleration. And note that this will, in general, be a vector quantity because this term is in the tangential direction and this term is in the normal direction. In general, there may be simplifications that we can make for our particular flow field. For instance, if there's no curvature, then this term is going to drop out, and we will just be left with this. If there's no curvature, then this term is not, if we have straight streamlines, then this term cancels, and this would be the local acceleration, and this would be the convective acceleration, and they would both be in the tangential direction. So our summary is that acceleration is caused by changes in both speed and direction. We know that from physics. The local and convective acceleration are terms that we use when we're expressing the flow field, the velocity, and the acceleration in an Eulerian approach in fluid flow. When the velocity field is specified, we know that this denotes the Eulerian approach, and we need to obviously choose the correct equations for solving the problem. And we will see this approach again when we talk about the Reynolds transport theorem in subsequent chapters. So that's it for section 4.4. There is an example that I will do in a separate video.